Okay, this is nuclear chemistry, the last unit, lesson 2, and today we're going to differentiate between various nuclear particles and we're going to write decay equations. So the first thing that you're going to need is you're going to need your reference tables, and we're going to be using table N, which is the selected radioisotopes table, and it gives you the decay mode and the half-life. We haven't talked about half-life yet, but it gives you the decay mode for each of the radioisotopes listed in the table. And we're also going to be using the periodic table because we need to know the new element that is formed. What I want to say is if you're looking in table N and you see something has a decay mode, let's just say, for example, 37K, potassium 37, which has an atomic number of 19. And it says that the decay mode is B positive, which is beta positive or positron. Say you don't remember what B positive is. Well, you turn the page and you look in table O and you find the B positive and you see that it's a positron. And a positron is also written like this, 0 plus 1e. So it's a positive electron. So you don't have to memorize it. You can just go from table N to table O, look it up, find your particle so that you can use it in the decay equation. So let's talk about the different particles and what happens in the presence of an electric or magnetic field. If I have a magnetic field, alpha particles would be attracted to the negative plate. They are not deflected as much as beta particles since they are heavier. So remember, alpha particles are really a helium nucleus, 4,2He. So the mass is 4. It's got a heavy mass, so that's why they're not deflected as much. And they have a charge of 2, positive 2. So the alpha particles are going to be attracted toward the negative plate because opposites attract. Your beta particle, which is really an electron, is 0, negative 1e. That is going to be attracted toward the positive plate because opposites attract. And your gamma particles, remember, have no mass and no charge. So they would not be affected by either a positive or negative plate. Okay, let's take a look at alpha decay first. First of all, I told you alpha decay is 4,2He, sometimes written as 4,2 alpha, which is kind of like a weird looking A. This is the transmutation whereby an unstable nucleus emits alpha particles. These are the important words. Alpha particles are products in the reaction, and the nucleus becomes smaller with less positive charge. Alpha emission is characteristic of heavy nuclei, especially atoms that have an atomic number greater than 83. Now this bottom part isn't as important. What you have to remember in alpha decay is, like with all of these that are natural, you're starting with one reactant and you're ending up with two products. One of which, in this case, because it's alpha decay, is an alpha particle. So in the diagram here, you see Pu, which has an atomic number of 94 and a mass of 240, very unstable, higher than atomic number 83, so its neutron to proton ratio is much greater than 1 to 1. It emits an alpha particle, so this is a product. And remember, so I'm going to put this over here, I'm going to write it up here, 4,2He. So this was emitted as a product. Remember that the mass and charge on the right must equal the mass and charge on the left. So if you have a mass of 240 here and the mass of He was 4, then this mass had to be 236. If Pu has an atomic number of 94 and He has an atomic number of 92, then this number had to be 92. Then we would go to our periodic table and look up element number 92 and find out that it's uranium. Alpha decay can be summarized as follows. As you can see here, the atomic number decreases by 2. So 92 is 2 less than 94. Therefore, the number of protons decrease by 2. The mass decreases by 4. 235 is 4 less than 239. And the number of neutrons decreases by 2 because of the atomic number. All right, let's do a couple of examples of what you would be expected to do if you had to write alpha decay equations. So you have 220 francium, and it's going through alpha decay, so my alpha particle is released. Remember that this arrow is like an equal sign. So that means our mass of our new element is going to be 216, because 216 and 4 is 220, and our atomic number is going to be 85, because 85 and 2 is 87. So we go to our periodic table, search for atomic number 85, and we find out that it's AT. Okay. The second one is also alpha decay because they're telling us, but if they didn't tell us, we would go to table N and we would find Rn 222, and we would see that the decay mode listed is alpha. Now they list it as just the symbol alpha, okay, in table N. So then what you could do is you would go to table O and you would see that it was 42He, and then you would write that in here. So back to this, 222 minus 4 is going to give us 218. 86 minus 2 is going to give us 84. We look up atomic number 84 and we see that it is PO, polonium. That's alpha decay. Beta decay. Beta decay is when a nucleus emits a beta particle. So it's produced. As a result of the nuclear disintegration, something said to undergo beta decay is called a beta emitter. The word emit means to basically release. So here you can see that cesium-137, which is also on table N, undergoes beta emission and turns into barium-137. Now, what happens in this process is that a neutron is converted to a proton and an electron is released. So let's just take a look at what's happening here. In the nucleus, I have a neutron, which is 10N. Neutrons have a mass of 1 and a charge of 0. And this converts into a proton. And a proton has a mass of 1, a charge of 1, and P. Well, in order for a neutron to convert into a proton, what had to happen? Well, there's no change in mass, but in order for this to balance out, this had to be -1, because -1 and 1 is 0. So 0, -1 is an electron. So, because this nucleus is so unstable, when it transmutates into barium, it's because a neutron is actually converted to a proton and a beta particle is emitted. So beta decay can be summarized. The atomic number increases by 1. So I started at 55, but my new atomic number is 56 because to balance this beta emission, that's what happened. The number of protons increases by 1 as well because our atomic number and our protons are one and the same. Our mass stays the same, there's no change in mass, and our number of neutrons has decreased by 1. Let's practice with a couple of beta decay equations. So here I have phosphorus 32 undergoing beta emission. So my new element is going to have a mass of 32 because this is 0, and my new atomic number has to be 16 because 16 and -1 is 15, which means that this is going to be sulfur. Here again, beta emission. I could look this up on table N and see that carbon-14 is beta emission if they don't give it to me. So this is going to be 14. This is going to be 7. 7 and -1 is 6. So this is going to be nitrogen. And one last example. This is going to be 214. And this is going to have to be 83 because 83 and -1 is 82, which is Bi. Okay. So we've done alpha, beta. Now we're going to look at positron emission. Positron occurs when a positron is produced during the conversion of a proton to neutron. So remember in this one we did neutron to proton. This is the opposite. This is going to be proton to neutron. So I have a proton. Here's my proton. It's going to convert into a neutron, which has a mass of 1, a charge of nothing because it's neutral. So this is going to be 0, and this is going to have to be +1. So a positron particle is emitted in this example where unstable sodium-22 transmutates into neon-22. What changes actually take place in positron emission? 2211 Na going to 2210 neon plus 0 plus 1 E. So here you can see that the atomic number decreased by 1, which means that the number of protons decreased by 1. The mass stayed the same, 2222, and the number of neutrons actually increases by 1, because since the mass is the same, if the protons are decreasing by 1, then the neutrons have to be increasing by 1. Let's do some practice with positron emission. So my mass is going to be the same. This is now going to be 18 because 18 and 1 is 19, and we looked this up on our periodic table. 18 is element argon. Here we have positron emission, 81. This is going to be 36. We look up element 36 and we see this is krypton. And one last one, 19 is the same. This is going to be 9, and element number 9 is fluorine. Very briefly, gamma rays, a highly penetrating type of nuclear radiation similar to X-rays and light. They have no mass and no charge. They are just a ball of energy. Makes them the most destructive form of nuclear radiation. Barium-137 stays barium-137, although it's very unstable and emits a photon. Remember from other units that a photon is a packet of energy. Okay, that's it for lesson 2. Have a great day.